The same thing you have to do when you want to calculate the input side. So open circuit the input side. Make the open circuit the output side. When you open circuit something, the current will go to 0. Voltage will be maximum. So put IR equal to 0 in the same equation, you get the other two parameters. Okay. So this is how you are getting ABCD parameters, and ABCD parameters are very, very important because they are defining our voltage ratio, current ratio, the Z value, and Y value. Okay. Right. So you are going to put it in the matrix format. You get Y. This is current ratio. We are assuming all ideal conditions with no losses. So IS and IR must be equal to 1. I mean, IS and IR must be the same so that the ratio is 1. Same thing here. VS and VR are same. So you get the ratio as 1. Put it in this matrix. So you can do AD minus BC. AD minus BC is coming from this matrix. AD minus BC should be equal to 1. Okay. So 1 minus ZY. ZY is Z and Y are opposite, right? So you can get the equation. Substituting the actual values, you can get the equation. Right. So this is for short circuit. Okay. Short circuit transmission lines, ABCD parameters are given by this ratios. Right. So when it is short circuit, I mean, this is the explanation of the same thing what I showed just now. Okay. So next is medium lines. Okay. So when it is short circuit, before we go to medium lines, we can say when it is short circuit, we are talking about this. Every section, okay, every section is equal to 25 kilometers. Okay, then you can apply this. Okay, so you get the equation for ABCD, the matrix. Okay, all right. So the voltage regulation. So after you get this, how do you do the voltage regulation? So how do you calculate the voltage? Why we are doing this ABCD parameters? Mainly because we wanted to calculate how much voltage is sent at the sending end, how much it is received at the receiving end. So receiving end voltage is given by Vs over A. So because A is here. A is Vs over Vr. Okay. So VR equal to Vs over A. Okay. So A is coming in the denominator. So whatever you input here, this based on the A parameter value, your R is going to be reduced. Okay. So what is A? A is coming from the elements that you are putting in. Okay. Same thing here. So voltage regulation is given by no load voltage minus full load voltage divided by the no load voltage. Okay. So sorry, full load voltage minus no load divided by the no load. So this is full load. Wait, regulation. Regulation should be given by the maximum value. Maximum value is no load. Okay, no load minus full load divided by full load. So this is regulation. Okay. So this is no load. This is full load divided by full load. Okay. So when it is full load, when it is no load, then your VR is determined by A. When it is full load, then your VR is whatever you are receiving is VR. It is not dependent on A. That is what we are looking at. Okay. So what is meant by no load, full load? No load means you are open circuiting the output terminal. Okay. Full load means you are short circuiting the output terminal. When there are more loads, it will drag maximum current. So when there is maximum current, then voltage should be 0. I mean, that terminal is short circuited. Okay. No load means there is nothing connected. So it is open circuit. Okay. So that is how this equations are formed. Okay. Right. So we can calculate the efficiency based on this. How much power delivered at the receiving end, sending end, and you can get the calculation, and you can include the losses in the line. 3 IR squared R. Okay. Right. So next is medium transmission line. So medium transmission line can be defined in terms of the kilometers, or it can be defined in terms of the voltage. Now it is medium transmission line or distribution line. Usually it can be transmission line or distribution line. In that case, you have to consider the capacitance. So when you consider the capacitance, there are two types of analysis. One is T network analysis, another is pi network analysis. What is T? T looks like this. Pi looks like this. Okay. So T network means you can have the inductance resistance combination in the series arm and capacitance in the parallel arm. Okay, this is called T network. If it is a pi network, then you will have inductance capacitance always comes in the series arm. This arm is called series arm. This arm is called parallel arm. Okay, inductance and resistance always in the series arm, whereas it will have capacitance in the parallel arm, two capacitances. So in this case, we say this is Z by 2, and this is C. Okay. In this case, this is C, this is half C. Usually say 1 over 2C. Okay. So this is how the in general T network and pi network are designed. Okay. Right. So let's look at the network. So you are seeing here, this is Z, here it is C. Okay, so when you are talking about L, you talk about Z. When you talk about C, you would talk about Y. Okay, so it is Y by 2, Y by 2. Okay, so then apply the two-port network philosophy. You can split it into 3 different sections. One section with this one, second section with this one, and third section with this one. So apply the same concept. Open terminal, closed terminal. Short circuit. Here you can short circuit it, open circuit it. Here you can short circuit it, open circuit it, short circuit it, open circuit it. And get the 3-port. For this one, you get one ABCD network. And for this one, another ABCD network. And this one for another ABCD network. Put them together, you will get the combined Y network. Combined ABCD parameter for medium circuit. Okay. Right. So we take the first section here. This is the basic equation we are using. Apply the short circuit and open circuit. So now apply short circuit and open circuit. So when you say open circuit, current is going to be 0. So put current equal to 0 in this equation. You get the values for A and C. In short circuit, so this gives you A and C. In short circuit, voltage is going to be 0. Then you will get the current. That gives you B and D values. Okay. So you can see in this medium lines, A, B, C, D values are different from the short circuit ABCD network. Okay. For this section. So do the similar practice for the other 2 sections. Look at here. The first section and the last section are the same. This section and this section are the same. Whatever you do for this section, you can apply to this section. Whereas for this one, you have to do a different way. Okay, take this one again. Open circuit. Open circuit, VR equal to, IR equal to 0. Again, IR equal to 0. Calculate A and C. And short circuit, VR equal to 0. Calculate B and D. Okay. And then for the third section, it is the same, like how you did it. Okay. Now put all the 3 sections together. You can get the whole ABCD parameter matrix. Okay. So this is how you have to analyze the circuit. It can be bigger one or it can be smaller one. You have to sectionalize it and apply ABCD equations. Okay. 2-port equations. Right. So then it's a long line. The long line also can be included. It can be it is not similar to the medium line. It looks like similar, but it is not similar because we are using the conjugate here. Okay. So, but the process is the same. Use the conjugate, find out the process, and then find out the equation. Okay. So what is this conjugate? Z star, Y star indicates, they indicate this value. Z star means ZC sin H. It's a hyperbolic, okay, gamma L, and which is given by Z over Y. Okay. So what is Z? Z is given by R plus J XL. Y is given by 1 over Z. Okay. So 1 over Z and with sin HL. Okay. So this is how you are doing the long transmission line. You can see here L is getting multiplied. Okay. So in every place it is ZL and YL. Length must be multiplied. So the values of the parameters are going to change with respect to the length of the line. Okay, that is what we are understanding. Right. So we are getting the long transmission line A and D equal to cos H gamma L and B equal to ZC sin H gamma L, where it is given by this Y parameter like this. Okay. So Z parameter is given like this, Y parameter is given like this. So what is gamma? What is this gamma? Gamma is termed as the propagation constant. And Z is the characteristic impedance. These are the very, very important terminologies. Characteristic impedance means this is very much related to superposition theorem. So how will you, what is meant by superposition theorem? Or I can say maximum power transfer theorem. Okay, so it's easy to go via maximum power transfer theorem. So what is my maximum power transfer theorem? Says hard recollection from maybe third term. Let me see your memory power. What is maximum power transfer theorem? What is meant by? I mean, anything you can recollect about that word? Just tell me. It's an electrical circuits topic.
The maximum power transfer theorem is like as long as the load is the conjugate of the damping resistance of the system, then you get maximum power transfer.
Yes. Any other way you can recollect it? So you define the theorem already. Okay, so I can put it in a very simpler way. When the load is equal, the value of the load is equal to the value of the source. The resistance at the receiving end and resistance at the sending end are same, then they balance each other. So you can transfer maximum power from source to load. And this is the important theorem we want to follow in power transfer. That is why we always want to have the load matching the source. Remember the first lecture I showed you, the load tappings going out from the tank with so many inputs and load. So load must match the source always. When the load is matching the source, then there is a power balance. When the power balance happens, then maximum power can be transferred. That is what it means. Okay. So maximum power transfer theorem is given by this characteristic impedance. So to match the load power with the source power, the impedance of the load power must be matching with the source impedance. So match the impedances at both sides, then you can get the power transferred through the lines maximum. Okay. Right. So what is propagation constant? Propagation constant is actually defining how the power is getting transported through the line. So you have this line. This is a transmission line. And you are transferring this power here. So when it gets into this node, it is encountered by capacitor and inductor. Both are energy storing elements. One can store energy in the form of current. Another can store energy in the form of voltage. So what is the effect of this energy storing element on the current? They can displace the current. They will not keep the current in phase with the voltage. They will try to put the current lagging behind the voltage or leading before the voltage. So the current starts to lag behind the voltage. As it goes through this line, the current starts to lag behind the voltage. So when the current is lagging behind the voltage, what it gives? It gives some angle, right? Some angle is produced. So that how much that angle can be? What is the maximum angle it can lag behind the voltage? So that defines how fast the power can propagate through the line. So propagation constant is actually talking about the speed at which your power can be transferred from source to load. The speed is basically defined by how much current lagging behind the voltage. So at the end, when the power is delivered to the load, we want both current and voltage there, right? If the voltage is not there, then what will happen? It will assume it as a short circuit. When the current is not there, then it will assume it as a open circuit. So how long it can wait for the, imagine there are two people running, okay? So the first person is called voltage, the second person is called current. Both are starting from the starting point at the same time. As they start to run based on their energy, the energy is basically based on the road, okay? So based on the road, voltage is going fast, current is lagging behind. But at one point of time, they should reach the end within certain time period. If the current cannot reach and only voltage can reach, then there is a problem. That means current somewhere it fell down, right? So what it means? Fell down means it's somewhere there is a disconnection, so that the current cannot travel further. So that indicates, so the time, the lagging time indicates, it can give you a lot of information about the fault. So we define certain time period. So that indicates within this time period, you should have voltage and the current received by the load. So that time period is nothing but the speed at which they run. If both are running at similar speed, not at the same speed, they cannot run at the same speed because there is a inductance in the line which can store current, so that it makes the current lagging behind the voltage. Okay, so it cannot run at the same time, but it can run at the similar time. Okay, so they have to reach at the destination at the same time, and not at the same time, but after certain time. Like if say 3 microseconds delay. Okay, the current is running 3 microseconds delay with respect to voltage. So when you are looking at the load, you will expect to see the current is received by the load 3 microseconds delay after the voltage. Okay, so just imagine a runway. Okay, so if the current is not reaching the receiving pole within that 3 microsecond, what will happen? What will you think? You will wait for 2 more microseconds. Okay, this is ideal. Somewhere it might have got something, lost some energy, so I can wait for 2 more microseconds. If it still doesn't come, then you will go back and check what happened, until which pole it crossed. What happened to other poles? Why it doesn't cross the other poles? So is it lying down in the ground somewhere between these two poles? That is how. Okay, so the speed at which is what defined by the propagation constant, and that's why the speed is nothing but time. The speed is, we are defining the speed with respect to time. Time is given by frequency. Okay, so that's why we want to look at voltage and frequency. This ratio is very, very important. Okay, the voltage, how much voltage is received at the receiving end, and at what time it is received. And this time plays a major role in the protection system, because all the protection systems can wait for 3 microseconds. I mean, 3 is a very random number I'm saying here. It is not exactly 3 which works with the protection system. Okay, I'm just saying for example. Okay, so 3 microseconds delay, the relays are good, the protection systems are good. Okay, current will come. We know this is the trial period. From the trial period, we know this is the time period. We can wait. If it still doesn't reach, then it can wait for 2 more microseconds. Backup relay. Okay, backup protection. If it still doesn't reach within 5 microseconds, then it will initiate the trigger. It will shut down everything and then send the crew to look for the fault. Up until which pole it maintained that relationship. After which, how much delay happened. After which pole, there is no follow-up by the current. It will go back and check section by section. Okay, so that is why we are looking at the voltage and the frequency. You get what I mean? Why voltage and the frequency? This ratio is very, very important. You understand? So whenever we turn on the generator to supply load, or whenever the load is increased and we want to match the source with the load, we'll be increasing the source. Okay, so when we are increasing the source, in the meter, we have to look at both voltage and the frequency ratio. So we will not be looking at how much is the input voltage, how much is the output voltage. Grid operators will not look at VS and VR, IS or IR. Their concentration will be on this ratio, V over F ratio. So we always look at V over F ratio, and if it is equal, they cannot make it 1 equal to 1, or they cannot make it 100%. If it is 100%, that means voltage and the current are working at the same time. That is not possible. So it can be below 100 and it cannot be below 98%. Okay, if it's below 98%, then the protection system cannot wait. They will trip the circuit. Okay, so this is the ratio they will look at. So propagation constant, coming back to propagation constant defines the speed at which it works and the angle at which it delays. Okay, right. So this is the example. I will walk through this example. Hope you might have done similar example in 243. So have you worked on ABCD parameters in 243? Oh, okay. Right. Then I'll take some time to walk on this example slowly. Okay. So what is more important here is how to calculate the parameters. That is more important. Okay. So the equations, I think you can go through the slides and you can learn how to derive ABCD parameters for various transmission lines. So now here it is talking about a 3-phase 765 kV 60 hertz 30 kilometer completely transposed line having a positive sequence impedance. Positive sequence, negative sequence, we are going to talk as the next topic in our next class. Okay, so don't worry about them now. So it is given as Z and Y values. So calculate the ABCD parameters. This is just the straight application of the formula. Okay, so A and D are given like this and B is given like this, and this is talking about 300 kilometers. So it's a long transmission line. Okay, yeah. So you can take the ABCD equations from long transmission derivation and you can calculate the values. Okay, so from this you can calculate the Z. You need to know what is Y prime and Z prime. Y prime is given by this equation, Z prime is given by this equation, and this equation is also having some constant here, gamma. The gamma is given by square root of Y times Z, and ZC is given by square root of Z over Y. This is characteristic impedance. This is the propagation constant. Okay, so apply the values here so that you can calculate the Z value, Y value, everything. Okay, so here we are using sin H gamma L, cos H gamma L. So it has to be expanded using the exponential theorem. It's a basic math. Okay. So expanded by the exponential theorem and then substitute it back. So ZC you can calculate directly. Z over Y, because Z is given, Y is given, you can calculate ZC, and gamma can also be calculated. Once you know ZC and gamma, then you can multiply it by L to get gamma L. Once you know gamma L, then you can apply it here. It is sin h cos h. What is sin h cos h? E power gamma L plus e power minus gamma L divided by 2 is your sine. E power gamma L minus e power minus gamma L divided by 2 is your cos. Okay. So substitute those equations, basic equations, and calculate A, B, C, D parameters. Okay. Cos h, sin h, and you can calculate this value here. Okay. It's a straight substitution of the values. So first thing you need to do is calculate ZC, calculate gamma L. Calculate gamma and gamma L, then the rest of the things are same. Okay, you want to take a look on this and then give me your feedback, or want any step to be expanded? I'm happy to do that. Okay, take a look at this. Okay, so you can calculate the B parameter for nominal pi circuit. So for nominal pi circuit, you can calculate the B parameter, and you can see it is giving you a little bit of larger parameter than the exact value. Okay, the angle is very, very important. Right. So this is the equivalent pi circuit. In the pi circuit, these are the formulas that can be derived for ABCD. Okay. So this is how it looks like. Equivalent parameters versus line length. So if it is a lumped parameters or distributed parameters, then your Z, Y values or Z prime, Y prime values are a little bit changing. Okay. So next we are talking about ideal lines. So ideal lines, there shouldn't be any loss. Okay. So when there is no losses in the line, so where the losses are going to happen, losses are calculated in terms of I squared R. And it is a three-phase line, so we calculated 3I squared R. So when you are calculating losses, what you are including? R. Okay. If it is a lossless line, what it means? There is no R in the line. Okay. So assume there is no R in this line. So your Z is R plus J omega L. So this can be Z equal to J omega L only, 0. Okay, this is lossless line. These are the assumptions that we are making to find out those values. Okay, so when you talk about lossless line, then we are assuming this step. So when you are talking about that, then your G also becomes 0. When there is no resistance, there is no conductance. Okay, so G goes to 0, so your Y is only given by the capacitance value, whereas your impedance is dominated by inductance and your admittance is dominated by 1 over J omega C. Okay. So your characteristic impedance is given by square root of Z over Y, omega L divided by J omega C. So you get L over C. Okay. So propagation constant, you get this one. Okay. So when you look at the propagation constant, it is purely imaginary number. Okay. Whereas your characteristic now impedance is purely real number. Okay. So we call this characteristic impedance also surge impedance when the line is lossless. Okay. For lossless line, characteristic impedance is same as the surge impedance. That's the maximum impedance a line can have. Okay. And it is a real number, and this one is a imaginary number. So why am saying repeatedly it's an imaginary number and it's a real number? Because real number, real impedance contributes to real power. How much real power is transported. When there is an imaginary parameter that contributes to the reactive power. Okay, so that's why this is important. Right. So the surge impedance loading. So this is what we are talking about, maximum power transfer. So when the load impedance is equal to the surge impedance, then you can transport maximum power because the line is lossless. When the line is lossless, whatever you are sending at the sending end must be received at the receiving end. That means there is a maximum power transfer happening. And it proves the maximum power transfer theorem in the other way. Right? So your load impedance and the surge impedance must be equal. So your surge impedance loading is given by ZC, characteristic impedance ZC. Okay. So this is actually power transported with surge impedance loading is V squared over Z. So Z here is a characteristic impedance. Z here is a characteristic impedance because that's the only impedance we know. Source side, we don't know the impedance, but we are assuming it's a lossless line. So maximum power should be transported. So if it is maximum power transfer, then your load impedance is same as the source impedance. So all the impedance are only ZC. So you are taking ZC as the only impedance in the whole line and you are including ZC in the calculation. Okay. So the nominal capacity of the power that can be transported is calculated from this value. So what is going to be nominal capacity of the power? Nominal capacity of the power meaning this is the amount of load I have. How much power I need to send. That is what it means as a nominal capacity. For all the time, the average load value, average load impedance is ZC. If it is ZC, then this is much of power I should have ready at the generation side so that I can run the load effectively without any failure, anything. Assuming all ideal conditions, no losses. Okay. Suppose if anything happens, so you are preparing the source to match the load. So balance. That is because I told you already, the lines are no storage devices. They cannot store any power. It's an inductance. You can ask me, oh, inductance is storing current. So what happens to the power? Pure inductance cannot store power. It can lag the old current, but it cannot store power. So there is no resistance. We are assuming lossless line R equal to 0. So power cannot be stored in the resistance because there is no resistance. It's only inductance. Pure inductance cannot store power. So all the power sent out from the source is reaching the load. So when you look at it from different directions, it is proving that maximum power is transferred. If you assume the line is lossless. Am I making sense? When I say line is lossless, then there is no resistance. When there is no resistance, then it's going to act like a pure inductance. If it is a pure inductance, it cannot store power. It can store only current, which makes the current lagging, but it cannot store power. So when the line cannot store power, where all the sending power is going to go? It's going to be delivered to the load. Am I making sense? So to happen the maximum power transfer theorem, according to maximum power transfer theorem, maximum power is transferred from source to load only when the load impedance matches the source impedance. So what is the only impedance that we are having in the line? Is a load impedance. Z. The load impedance is the only value that we are having because load impedance matches the source impedance. So you have to prepare your source accordingly. So whatever the type of generators you have, that is what all the grid operators are doing. All the time they want to serve the load under this condition and keep the generation stations ready, and they make the purchases accordingly. So the long time purchase, a year ahead purchases are happening based on this. So they know how much is ZC. So this is the amount of load I have average all the time throughout the year. So I make available for the purchase. So that is the cheapest purchase they can do. They send out the bidding a year ahead, and then they will buy all this, make arrangements to supply power whenever needed, according to the, with some headroom. Like suppose if they want to deliver like 20 gigawatts of power, then they will have arrangements with a nominal capacity of like 25 gigahertz. So they will make arrangement with different sources. It can come from thermal energy, it can come from gas turbines, it can come from wind turbine, it can come from hydro, whatever you name it. Okay, so they will buy different sources. Maybe name 5 sources. They buy 5 gigawatts from each source and keep ready for 25 gigahertz throughout the year. Sometimes when abnormal condition happens, like a heavy winter, heavy summer, then it may go beyond the headroom. Like the power needed by the load, ZC value can go high. So ZC value can rise so that the nominal capacity of the power requirement may increase from 25 gigahertz to 30 gigahertz. So at that time, they will do the prediction. Like, so now we are entering into winter, right? So they will do predictions for the worst winter conditions based on the region. If we take Oregon, then we will get the ice storms or peak ice period, snow period is January, right? So we will people will do the calculations based on the weather. They know how much the power is going to increase in September. So they will purchase power in September based on these predictions. That's kind of a 3 months before purchase. That's a little bit costlier. They will not get that power. They will not buy that power. They will just pay some advance, make it ready. I mean, they'll say, okay, you can have your power. You can give it to anyone you want. But when I ask, you have to give me that power. So they just pay a token advance for that. And they will make sure that these people are ready to give them the power whenever they require. Okay. So they will reserve it. So that's we call it as reserve capacity. Okay. So they will reserve it. And in addition to that, they'll make a day ahead prediction. Day ahead prediction is what happens. I mean, they may expect some windstorms, but it may not happen on the exact day. Okay. Sometimes when it happens, it can be very severe. So every day before, a day before that, any day, they will make some calculations based on this nominal capacity and the load, and then they will make purchases. And there's a last purchase. The costliest purchase they do is 15-minute window. When things are happening at that moment, they will start to purchase. That's the costliest purchase. Any grid company wants to avoid that purchase. And that is where the electricity market commission agents will play their role. That's like a stock exchange for them. That's the most profitable time for them. Okay. So all the generation companies will have some headroom to supply power during that time. 15 minutes window, they will keep some energy because that's the profit. The year ahead purchase is kind of selling whatever they produce, they sell. They'll make a profit, but not a big profit. But the day ahead projection and 15-minute window projections are the maximum profit periods. That's when they play. Okay. So yeah, so we are deviating to many other stories, but so that is what the nominal capacity is calculated. You get what I mean? Okay, good. So this is how it goes. Like how much is the power transfer and how much is the capacitance and how it depends on the capacitance and inductance value. Okay. So when the until here, the inductance plays the role, Z value plays the role in calculating the power. So when you are transferring low power, you just need to look at only the Z value. Once it goes higher power, then you have to look at the capacitor. Capacitor means when you talk about capacitor in the power line, you are talking about the reactive power. Okay. So lagging reactive power, leading reactive power. So when the power goes, when the power transfer is increased, then you have to compensate it by the capacitive compensation. You have to supply it by capacitors because the real power cannot travel longer. So it needs to be added with the reactive power so that you can transfer it in terms of MVA. Okay, that is what this curve is talking about. So under surge impedance loading, the line consumes as much reactive power as it generates. Thermal voltages are equal. So that's why under certain surge impedance level, you don't need capacitors because it's balanced. Reactive power travels back and forth, so it is balanced. The forward moving reactive power is balanced by the backward moving reactive power, so it's balanced. So you don't need to really worry about turning on the capacitive compensation. But once it goes higher than the surge impedance loading, then you have to look at the capacitance and then look at the reactive power and then turn on the capacitor compensation circuits. Okay, so that is when they look at. So what is the power need? Remember the Ohio scenario we talked about. So they talked about the power transfer, the how much power transfer happening between different regions. So when the power transfer happens between different region exceeds the one, it must be equal. When it is equal, they don't worry about the reactive power compensation. When it exceeds, that's the time they turn on their capacitive compensation. And when they run out all the capacitive compensation circuits, then they will start to buy reactive power from other side. Right. So the wavelength, signal's wavelength is a physical distance it will propagate in the time of one period. So gamma, I told you, it's a distance it travels with respect to time. How long that current is following the voltage. Okay, how long, how many poles it crosses. Okay, so physical distance it propagates with in the time of one period. Okay, so that is what we are talking about gamma, which is giving us this ratio V over F. Okay, right. When the period of transmitted voltage or current exceeds the propagation time, then it is considered as electrically short. Okay, so that is more important, and we have to look at this ratio always. So gamma value gives us the ratio value that we need to look at for protection circuits. Right. So this is the angle we are talking about. When there is a when current is following the voltage, it makes an angle, and it also brings the angle between the voltage sending end and the receiving end. So that angle is actually leading to sending and receiving end angle difference. So what it means is because it is traveling through inductors and capacitors, the sending end voltage and the receiving end voltage will not be at the same phase. They don't stand at 0 degree. That will be an angle difference. So the angle is another important term that we need to look at. So now we are talking about what are the terminologies that we need to look at. Okay, sending end voltage, receiving end voltage. And then we have to look at V over F ratio. And then we are talking about the angle, the dou. Dou is the angle between sending end voltage and the receiving end voltage. Okay, so these are the important terminologies. We need to look at these things along with the real power and reactive power. Reactive power is usually given by the letter Q. Okay, so along with real power and reactive power, you have to look at this frequency and angle. Okay, so these are the important terms. So this is called load angle. Why it is called load angle? Because look at this angle is formed based on the voltages. What is this voltage? This is sending end voltage. This voltage is receiving end voltage. Receiving end voltage is defined by the load. Okay, so we are taking that as a reference and drawing sending end voltage, because sending end voltage is coming from the generators. How much generators you want to turn on to match the load. Okay, so that's why sending end voltage is here. So the angle is dou. So when when this voltage is increased, okay, when this voltage is increased, it's going to ask for more voltage from the sending end. So when it is asking for more voltage, this angle is going to be changed. Okay. So the angle is defined by the load. Okay. That's why it's called load angle. Right. So this is how it looks like, the real power. This is the maximum power we are talking about. Power is given by the sending end. It is P equal to V squared R. Okay. R or Z. Okay. So in this case, Z equal to JXL. And V here is V squared. So we can split that V into sending end voltage, receiving end voltage divided by Z. Okay. So maximum power happens when the angle is at 90 degree. When it is less or below or higher, then you will see the curve, power curve here and here. Okay. And that power curve is not allowed to go very low, here or here. Okay. That is what it shows. So sending end and receiving end, it depends on the line length. Okay. Line length is affected by the inductance. Okay. So inductance at the sending end, inductance at the receiving end. So this is when it matches with the surge impedance loading, your VR equal to Vs. So if there is no load, then sending end will have higher voltage, receiving end no voltage. So the curve goes like this. As the load increases, then you are seeing it like this. Okay, so these are the curves. So P is given by these values and the angle. Okay, sending and receiving end is producing an angle. So that angle should be included in the equation. In this equation, we are including the angle, which is a sine angle, because this looks like a sine. Okay. So theoretical maximum power transferred is given by this equation. So this equation, you can see the detailed derivation of each of these results in the textbook. Okay. So VR Vs over Z, and VR is defined by its, VR and Vs are defined by its ABCD parameters. And so you have the sending end angle and the receiving end angle. Okay, Z and A. Okay. So next is the steady state limit. So what we have seen so far is when you can transfer the maximum power. So when power can be transferred is called as maximum when the sending end voltage is equal to the receiving end voltage under theoretical conditions. Okay. So, but the sending end voltage and the receiving end voltage may have different angle. Okay. So that angle is called a load angle. And the speed at which the sending end voltage is received at the receiving end, then that is called propagation constant. Okay. So we talked about V, F and the angle theta or dou. Okay. Now, so we make sure that the maximum power is transferred, nothing is changed to the load, and the source is meeting the load, everything is going good, and surge impedance is balanced. Okay. Surge impedance is happening with the characteristic impedance. Surge impedance is given by ZC. Okay. So we call SIL, surge impedance loading is happening. Surge impedance loading means we are meeting the impedance at the load and the impedance at the source. Both are same. Okay, maximum power is transferred. Theoretical maximum power is transferred. So when the power is transferred, power is going through, every time I'm repeating this, okay, power is going through inductors and capacitors. So when the power is going through the resistors, it will look like this because the voltage and the current are constant. So your power is also constant when it is a resistive network. When it is an inductive network, then it's going to have exponential increase and exponential decrease. The same thing, So when you say exponential increase and exponential decrease for the inductor network, then the current will have this characteristic. When you're talking about the capacitive network, then it will also have exponential increase, exponential decrease, but it is voltage. Okay. But here, our transmission lines are combination of inductors and capacitors. So both current and voltage will oscillate. They will go through exponential increase and exponential decrease. But what will happen is, when you put them together, they will go like this. That is how we get the sine wave for our waveform. Okay. So that is why you are getting a sine here in the equation, theoretically speaking. Okay. There's mathematical justification is given in the textbook. Go through the textbook. I'm just trying to explain it from what we understand as power and inductors and capacitors. Okay. So when you put the oscillations together, you get the sine wave. So this sine wave is coming from this exponential increase, right? Exponential increase means it's going through the amplitude is increased with respect to time. So when you look at the waveform is not going to look like this with equal amplitude all the time. It is not like that because it is coming from this curve. The voltage and the current are coming from this curve. Okay. So what will happen is, when you start the voltage, when you start the power, it will go through like this and then it will stabilize. It will stabilize to normal value. So why this curve is happening? Because the device which is sending out the voltage is not a constant voltage source. It is an electromechanical device. So electromechanical devices like generators and motors, which are influenced by their own inductance and capacitance, their current will go to peak to aid the starting torque. So current will go to peak, and then once the torque is matching with the machine's torque, then it will start to stabilize. Okay. So that's why the voltage is going like this. The voltage or the current will be going like this. And it is allowed. So every time you see there is an increase in the load increases. Okay. So it is a normal day, but the peak time comes. So when the peak time comes, there will be more loads added to the system. So it will start to drag more current. So you will see there is an increase in the current. So the waveform of the current will be going like this, and then it will stabilize. Okay. And then it will stabilize because the current is coming from the electromechanical device. So it will start to increase to a higher value and then it will try to balance. So this is a very, very important thing that we have to remember. So when the current is swelling, so this is called current swelling. Okay. When the current is swelling in the line, it can be understood as a fault current. There is a possibility that it can be understood as a fault current. But we need to differentiate between increase in the current because of the load versus the fault current. How we can identify the difference? Go ahead. Whatever coming to your mind, just tell me, because I just want to break your sleep. I'm not expecting expert answers, just want to be alive in the class. Yeah, good answer. Any other thinking? He said time.
I was kind of thinking, like, essentially when the motor starts up, we know like how much time it'll take to get to the equilibrium.
Stable. Yeah.
And, but with a fault, if it exceeds the amount of time, we then know it's a fault.
Right.
I will look at the peak of the current.
Okay, the maximum value.
The maximum value.
Okay. Yeah, that's another point.
Sometimes if the value is too much,
yes,
as we tell you,
correct. That's also one point. Yeah, both are good points.
be if the load resistance was as low as it could possibly be, like if there was like a short. So what that current would look like with respect to the multi-gray.
Correct. Yeah, that is also another point. Yeah, good. Yeah, so you put everything, all the points are down here now. So you are looking at the difference. So how much, so we have to allow uh, uh, the system to stabilize. Once you start, it will definitely go to its maximum level and then it will stabilize. It's like a child. So once you trigger the child, show all the energy, and then the child will stabilize and perform normally. Same thing. So when the load is increasing, the generator starts to put more current into the system so that it looks like swelling, but it should stabilize within the time. Okay, it should stabilize within the time. At the same time, we also have to look at the peak versus how much it requires. Okay, so the peak should not exceed the maximum allowable level that the lines can carry. Okay, lines are limiting it. So we have designed the lines, the cables, for particular amount of current. If it goes above that, then there's going to be more losses in the line, and lines may also feel loading. Okay, so the peak, the time, and everything. So we want to see the curve stabilized here. Okay, so how much time it takes to stabilize determines the time at which the relays can operate. Okay, so for any system, you should know what is the maximum load. What is the maximum load? And you should add some more room for that. Suppose you say the maximum load can be like 100 kVA, right? Then you have to have a room for a little higher room, like 150 kV. Then you will design everything based on that. I told you already, you have to do the design from the load. So design your lines to carry 150 kVA, make your generators available to supply 200 kVA. Okay. Then if the curve goes to, then you can do all the calculations. Your propagation time constant, the angle calculation, everything can tell you how long it's going to take to stabilize. So based on that, you can allow your protection devices to work. So protection device will not trip the circuit until that time is passed, if the current is within that peak value window. If the current is within that peak value window, if the peak is within that window and it takes more time to settle down, then it is a fault current. Okay. Another way, the current can go to a very high value for a shorter period of time, and then it can stabilize, but still the relays will trip it down because the current has gone to a very high value. So that's why when you're talking about the protection relays, we always talk about the current versus time. Okay, so we keep the current in the x-axis and time in the y-axis, and then we draw the curve. It's always the comparison between the current and the time. Okay, so steady state stability limit. Steady state means the stable state. Stability. So when it reaches the stable state, it has to reach the stability. Stability means it can still oscillate. Not necessarily it should maintain constant. It can oscillate, but it should be stable oscillation. Okay, so it can reach the steady state and it should be stable. So what is the limit for that? That limit is going to impact on our load. Okay, so this is given by this formula here. So sending end voltage, receiving end voltage, from that we can calculate the steady state limit. Okay, it is affected by the angle. Look at the angle. Okay, right. So do we want to take a break now? 2:30 already. So let's take a break. So we will meet at 2:45 and continue this calculation. I think I have few more calculations here. I'm not sure if I can able to start the, let's see how far we can go. If I cannot start simulation today, then we can do simulation next week.
Doctor,
Yes, I said.
could you put the discussion that you were talking about in the chat? Because I keep forgetting and I can't find it in the lecture.
It is in Canvas. You're talking about the discussion board where I put the
Oh, it
lectures.
is?
No, I think he's talking about what the actual topic for the discussion today.
Oh,
Yeah.
okay. Okay, got it.
Okay. Thank you.
Mhm. Discussion topics usually I talk about it in the class. I don't put it in any lecture or anything. Yes.
So obviously, at the end of this lecture slide, if there are these exercises, I'm on this one. Obviously, I see from when you do it, you just have some nominal value for the wavelength, and then you can calculate that by the inverse of the product of the frequency times the propagation delay. But you need to have the inductance and capacitance.
The maximum power transfer, thermal limits are there, and thermal limits are affected by many. Most of the time, the thermal limits are affected by the temperature and the current. Okay, and then angle limits. We are talking about the dot angle and then voltage. So here we are talking about mostly the current. Okay, right. So theoretical maximum power delivered. So we talked in this question. We talked about the limit, steady state limit. When you say steady state limit, we are talking about the megawatt of power. Okay, here we are talking about the power delivered, maximum power delivered, assuming for the same case. Okay, theoretical maximum power delivered in per unit of SIL that the line can deliver. Okay, what is the maximum power the line can handle? So you need to know what is the maximum power that can be transported. What's the maximum power the line can handle? Okay, so the lines can handle can be calculated from here. Okay, so your theoretical power is coming from P maximum per surge impedance loading. So P max divided by surge impedance loading. This is per surge impedance loading. Okay, you are dividing it by surge impedance loading. So you need to get what is the P max value first. P max value is given by this formula. Maximum power transfer is given by this formula, and you can get per surge impedance loading. So when you say per, it's per unit. Okay, so this is the maximum power per unit. So this theoretical maximum power transferred is different from, look at here, this is the value you are calculating. So this value is different from this value for the same voltage Vs and VR. You understand why? We are talking about the steady state power here. This is steady state power. Steady state power. Here we are talking about the maximum power. Maximum power. So we are seeing a little bit difference between the steady state power and the maximum power. It can oscillate. It can come to a stable state. So that's the maximum steady state power we are talking here. Here it is talking about the maximum power that can be transferred. Maximum power that can be transferred. These are the two different powers. Am I making it clear? Any questions? All right. So this is the maximum power that can be transferred. Okay. Right. So when you say maximum power that can be transferred, we are including the Z values here in the equation and the angle at which the power can be, the ascending end voltage, receiving end voltage, and the angle, everything is included here. Whereas when you are talking about the steady state power, we are using only the surge impedance loading. We are matching the load impedance with the source impedance, and we are calculating the limit. We are talking about the limit here, and this is actually the amount of power that can be transferred. Okay, go ahead.
So the maximum steady state power, that's like as much as the line before.
Yes, that's the ceiling.
Okay.
So when you
above that would be this is all.
yes, usually, I mean, theoretically speaking, for understanding wise, what you said is correct. But usually, fault is not calculated based on the power; it's calculated based on the current and voltage. Separate entity. Power is like kind of a combined one. Voltage and the current combined, but we look at it differently.
What about that ceiling?
It's a ceiling. Yes, correct. So the theoretical steady state limit is talking about the ceiling, as Tony said. This one is talking about maximum power, is talking about the amount, quantity. Okay. Right. So now this is the practical line loadability and percentage of voltage regulation. So practical line loadability here refers to how much your lines can handle. Okay. So you can transfer, you can have the capacity to transfer maximum power. You can even add loads to handle that power. But what is the line capacity? What is the line loadability? Okay, so that is what we are talking about here. So when the 300, the same problem, it's continuing. Okay, so 300 kilometer uncompensated line has 4 conductors. The conductors that we talked, okay, in our last class. Sending end voltage is held constant as 1 per unit. Determine the line loadability. Okay, so if the receiving end voltage is only 0.95 and the angle is 35, then what is the line loadability? Line loadability means there will be losses. I mean, we calculated the other things with the low loss, right? Lossless lines. Suppose if there is a loss in the line, it is going to be reflected in terms of I squared R loss. So that power is going to be dropped across the line. So what is the maximum loss that the line can handle? That is what we are talking about. Okay. So practical line loadability. So we are taking this equation here, the maximum power, and in this maximum power equation, the same maximum power equation that we talked about here, the maximum power transfer. Okay, same maximum power, but here we are talking with respect to the loss. Okay, so because the sending end voltage and the receiving end voltage are not the same, so the remaining power is going to, I mean, after the losses, this is the amount of power that you are going to transfer. Okay, the dou is also changed here. Right. So full load receiving end current is 0.986 power factor, leading at practical line loadability. So how much is the load current received? Full load current. Okay. So this is the amount of load current that you are looking at. And voltage regulation. Voltage regulation is full load minus no load divided by, no load minus full load divided by full load. Okay. So you have to calculate R full load and then voltage full load and then voltage no load. Voltage no load and then calculate the percentage regulation. So this is the percentage of regulation. So this is the approximate line carrying capacity. So each line is carrying 1.2 kA means 4 lines should carry 4.8 kA. So we are defining the current capacity of the line, voltage capacity of the line, power capacity of the line in this example. Okay. So I'll give you a few minutes. You can go ahead and take a look on this question and then tell me your question, your understanding or your questions. Okay. Any questions? Do you need more time? Okay, is it making sense? Right. So, what we are talking today is from the looking back into our first lecture. In the first lecture, we talked about a higher scenario and we said many issues. Power limit, we talked about the power limit. We talked about the reactive power, the deficiency of the reactive power compensation in the facility. We talked about the loads increase, and then we talk about the technical things. Okay, so technical things we are not going to address in this lecture. We are going to address it in the production side when we are talking next term. Okay, but apart from that, we talked about the fault. So, apart from the fault, we talked about all the three other items today. So, we talked about power. How do they calculate the power? How do they estimate how much generators they need? So, based on the load. So, how do you estimate the load? So, load is coming from, I mean, you have to balance the load impedance with the source impedance and see what is the rating at which your lines are designed, and you should be able to transport that much power from the source to the load, and your line should be accountable for the losses. Okay, so how much is a stable, how much time it takes to reach, how much time it takes to become stable, everything under normal condition. Okay, so under normal condition, these are the parameters that we need to look at. The impedance we need to calculate. The impedance we are calculating, surge impedance we are calculating from the amount of load we are adding to the system. And from that, we have to match that load impedance with the source impedance. When both are matched, then we call it a surge impedance. And then we have to match the power accordingly. So supply as much power as the load needs. So when the power is supplied through the lines, we have to take care of the lines. Is the lines capable of carrying that much power? That's another thing that we have to look. If the lines are capable, or if the lines are not capable, then you must define how much lines that you need to add to transport that much power. So this is what we have talked about so far. So we talked everything about the normal power transfer. Now we are going to talk about the reactive power. That's the case happened when all the AC units were turned on, right? Everything was going good until the heat went very high, and then people turned on their reactive power. That reactive power, I mean, people turned on their air conditioner units, which contributed to the inductive power, inductive nature. It increased the load's inductive nature. So when the inductive nature is increased, when the inductance is increased, what happens? The angle becomes wider. The power angle becomes wider, and then the sending end voltage, receiving end voltage will not be equal. Impedance are not matching. So if the impedance are not matching according to this curve here, we have to compensate it by the capacitors. So how do you calculate the capacitance? So compensating by capacitance is called reactive power compensation. Okay. So now we are moving on to that section. So how to compensate it by reactive power? So there are different types of reactive power compensation methods. Okay. All of them are going to do ultimately the same work. How much capacitance they want, they are going to put that. But there are different ways to do that. So these are the normal capacitance compensation, whereas these are advanced technology, which are working based on the thyristor concepts. Okay, right. So this is how we are talking about the switched capacitors and reactors, and it is controlled by thyristors in the control room. Okay, right. So reactive compensation. So you can see the inductors and the capacitor banks in the yard. Okay, substation. So now this example is talking about how much reactive power compensation we have to compensate. Okay, so it's talking about the ideal shunt reactors connected from each phase conductor to neutral at both ends on the sending end and at the receiving end of the previous example. Okay, it is providing 75% compensation, and the reactors are removed during the heavy load conditions, similar to our Ohio case. There's not sufficient reactive power compensation available in their facility. So that's what they were talking to each other, right? In that conversation, send me more war. They say, oh no, my line is sagging. I'm already seeing everything is going down. So that is what it's referring to. There is not, the reactors are removed, meaning there's not much reactors. So in that case, the full load current is 1.9 kA at unity power factor. So it is increased to 1.9 and at 730 kVA. Assume that the sending end voltage is constant. Sending end voltage is not increasing. So what is the percentage regulation of the uncompensated line? And how much the equivalent shunt admittance and series impedance you need to put? How much reactive power you need to compensate by using L and C? And then percentage of voltage regulation. So once you put L and C, it will become a compensated line. Then after you compensate it, what is a voltage regulation? Okay, is it improving or not? That's what we are looking at here. Right. So we are doing the uncompensated line voltage regulation first, similar to the previous case. We did it already using this equations, and then shunt reactive compensation. So shunt reactive compensation, we are going to calculate the L and C value. So L and C are coming from Z and Y. Okay. So take the previous Z and Y values, calculate the no, I mean, this is actually, here we are calculating the full load and no load voltages. And then we are, okay, so this ends the percentage of voltage regulation. So answers the voltage regulation of the uncompensated line. So calculate the voltage regulation of the uncompensated line, and then calculate the Z value and Y value. Z value and Y value. From that you can calculate the L value and C value. Okay. So this is the Z equivalent, this is the Y equivalent for 75% compensation. So you take the same Y and Z values, and then it's 75% compensation, so multiply it by 75. Okay. Then using this new Z and Y value, calculate the new compensated line. So earlier the voltage regulation was 12.69. After compensation, 75% compensation, you are reducing the voltage regulation to 6.77. Okay. And now the next question is, suppose if you want to transfer more power, so how do you determine the number of conductors you require? Okay. So with one line, sorry, there is a spelling here, one line out of service, for the following cases, identify the, determine the number of 3-phase 60 Hertz line required to transport this power. How many lines you want, okay, from the electrical point of view. So first line is 345 kV with the ZC as 297. Second is 500 kV with ZC of 277. Third is 765 with the ZC of 266 with VS is 1 per unit and VR is 0.95. It's 95%. So when you say 100%, you receive only 95% at the end. Okay, and dou is given as 35. So for this case, we are using the same power, neglecting the losses, calculate the power, maximum power transfer. Okay. steady state limit. Under steady state limit, calculate the values. So the gamma value should be given here. Gamma value should be given as 5000. Actually, wait. It is given here as 500 kilometers. Okay. So the 500 kilometers, it should be 5000 kilometers. Okay. So this is what determining your gamma value. So the distance determines the gamma value. It's a propagation constant, right? So distance relates to the gamma value. So you're taking the gamma value and putting it here. And then do this. I will correct it. So the length is 500 kilometers and the gamma value should be given here as. So in this question, the gamma value should be given. Okay. So substitute in the line, how much power you want to transport. Calculate the maximum stable limit power. Okay. So this is per line. But how much they want to transfer is 9000 megawatt. So divide it, you can get the number of conductors. So if you are transporting only 372 megawatt per line, then you might need 26 conductors, 26 lines. Okay. Suppose you increase the capacity of the line. Look at here. So the line length is going to 500 kilometers. And so if that is so, then your megawatt of power is increased. Okay, so this is increased here because it's a 500 kV line. So there is a typo here. So this is 500 kV line. Okay. So I will correct this too and repost this lecture. Okay. So when this power is increased, then your line is reduced. That means each line is carrying more power. Okay? Like that you can do for the other one. So again here, this is 765 kV. Right. So your line is reduced to 6. So this is how you are calculating the number of conductors. Okay. So this also taking it back to the same Ohio condition. So you want to transport 9000 megawatt of power at 745. So each line is 765 kV line. Okay. The capacity of each line is 765 kV and you want to transport 9000 megawatt of power from this load to this load. And you know that for sure you want 6 conductors in that case. So if one conductor fails, happen in Ohio case, if one conductor failed, what will happen? It cannot carry the line. Okay, it cannot carry 9000 megawatt of power to the load. So the load is not getting the expected voltage and the power as it required. So what will happen is our system is designed for automatic regulation control. So what it will do is it will put that extra power, extra line, because one line is already failed. So all the loads which are connected to that line, the additional, so it's calculate how much, so multiply it by 5. So the only that much power it can transport. So there are some loads which are not getting the power, enough power, right? So those loads will be transferred to another line, another set of lines. So that will add as a loading to that line. And then it will start to ask for more power because the load is increased on that line. It will ask for more current and more power, which will ask for more reactive power. So look at here. If the lines are increased, so if the power transfer is increased, you add more line, more load to that, then the power required by that load is increased, right? Once the power is increased, then you have to compensate. Reactive power requirement in that line will increase. So you have to turn on more capacitors. And if you run out of capacitors, then it will lead to that scenario. Is it all making sense now? So this is how you are starting. So you are starting from the load, going back to the source. So load, I need this many loads. Estimate how much voltage you want to send from the source. Match the sending end voltage with the receiving end voltage by matching the load impedance with the source impedance. That's called surge impedance, loading. Then If that is matched, then you are making sure maximum power is transferred. When maximum power is transferred, you are making sure all the number of lines required is active. So I want to transfer 9,000 megawatt. I want 6 conductors. If each conductor is carrying 745 kV, then all the lines should be intact, perfect working condition. Even though it's a very hot climate, if it requires more power, still can be able to transport power because we have the limitation on the lines, right? But if one line fails, then it will add that load to another line that will ask for more reactive power and that will make the system fail. Am I completing the story now technically? Right. Happy that you got that point. So these are the important things that we need to do when we are doing the designing. This where it goes is it is going into the design, electrical design of the lines, electrical design of power transfer. So these are minimum calculations that we'll be doing. Okay, it is not talking about the conductors. Okay, so I want to make sure here, don't think about you are designing the conductors, you are designing the power transfer, how much power transferred from one end to another end, how to make it stable, how to how much reactive power you need to keep it ready to compensate that line when the power goes to its maximum level. That is what we are working on. Okay, right. So I think I can finish it here. What's the time now? 3:12. So let me stop here and open the session for discussion. So these are the things that we talked and we completed the whole picture now. And from next class, we will start talking about the last term in the higher scenario is a fault. How fault is identified, how you can identify the fault, what are the different types of fault, how you can identify it, and how you can, what are the effects that faults can have on the line? What is its effect on the current? What is its effect on the voltage and the power? Okay, so those are the things that we are going to talk from next class. Right. So I will walk through these examples next week, Power World examples next week, which are closely related to the problem that we discussed. We took one numerical example and we discussed everything with respect to that example, right? So this exercise, this simulation is also related to that particular problem. Okay, we will see how these numerical values are having effect on the simulation, and you can perform similar thing in your project. Right. So this is homework 3. I think homework 3, right? Okay, so this is homework 3 problems completely based on this examples that we discussed today. Okay, right. So I'm going to stop here and let's open the discussion for about underground overhead cables. Are you ready? Need more time?
So I just wanted to ask about homework 3 real quick, because it's going to be book problems.
Mm.
Okay. There's a zip file for homework 3 on.
Oh, okay. I will talk about that because that one is talking about the design of lines. Mm.
Sorry, I missed that. Did you just say that the homework was the problem was assigned in the lecture science?
Yeah, that is what I'm looking at here. Okay, so I'm looking at here the that this is a simulation problem. Mm, okay, I will fix it and tell you. Okay, so this exercise problems, what I posted in the lecture slides, I really want you to work on those exercise problems, but not as a homework. Okay, just as a practice problems. And I can give you the solution. We can discuss the solutions maybe 2 weeks from. I mean next week, because it's just a exercise problem. It will help you to prepare for the midterm exam or final exams. Okay. So for next week midterm exam, what are the portions I said last week? Does it include this week? No, until last week. So we are going to talk about the reactive power compensation. I mean reactive power, active power, reactive power, all those problems, and then we are going to talk about the design of the conductors. Uh, the ACSR conductors and the calculations we did in our last class. Though it's a review of 243, but it is good that we will go through it in the exam. Okay. So your midterm exam will have problems as well as theoretical questions. Theoretical questions mostly based on practice quizzes. Problems, you can look at the lecture notes problems and start to work on the exercise problems given in the book and ask me if you have any questions. Okay. And this week, whatever we discussed the problems today is not going to be included in the midterm exam. It will be included for the final exam. Okay. And I will fix this homework and then I'll give you more time to work on this homework, and I'll talk about this homework problems next week. These are mostly related to next week content, how to do the simulation calculations behind the fault identifications. Okay. And there is another thing I want to show you is plotting the PV curve from Power World. Okay, so we will talk about those two things in our next week. Next week for sure we will spend more time in Power World. Okay, right. So let me stop here, and yeah, are you ready for discussion today, or shall we make it for next week?
Just to clarify, so right now we don't have the homework 3 assignment yet. You're going to upload that.
Yes.
And then also, I was wondering, before the midterm, are we going to get corrections?
Yes.
For homework 20?
Correct. You are going to get.
And for homework 1, I'm still not seeing that there's anywhere to submit that on campus.
You haven't submitted it yet?
It's still locked.
Okay.
So remember you said that you extended the date.
Yeah.
The submission page on campus never opened.
Okay. Thanks for reminding me about that. So can I keep, I think Alfred, you also need extension for homework 1, right? So can I keep it until when?
Homework 1? I emailed you the homework 1.
I'm extending it now. So can you put it in the Canvas page?
Yeah, I can do that. Homework 1, right?
Yes.
And yours, okay. I did have a question.
Go ahead.
About. So there was a quiz, right?
Quiz 1?
Yeah, and I was abroad. I was international that when the quiz was open, and I did not get to it.
Oh, okay.
I was in
I will.
Mexico.
Okay. Can I make the quiz open for you tonight? Maybe 6 o'clock?
Open from 6?
Until 8?
Sure, yeah.
All right. Or you want to take it tomorrow? So which day? Today or tomorrow? Which day is convenient for you?
Let's do tomorrow.
Okay.
Let's do tomorrow from I mean you can do it earlier tomorrow.
Morning 10 o'clock?
Yeah, we can do from 10.
Okay. Good. I will open it up for 12.
Did you, maybe I missed a little bit. Did you say the points, what's going to be included in the midterm?
Midterm includes portions until last week.
Till last week, okay. And what kind of study can we do for the midterm? Is it the quiz
The
1 and
problems,
quiz 2?
yeah, the problems you can practice the problems that we discussed in the class, and also the exercise problems which are similar to what we have done in the class.
Okay.
And homework 1 and 2 will help you, and then the practice quizzes. So it's
Sounds
a
good.
combination of calculations and theory.
Okay. And practice quizzes, which ones? There were multiple of them, right?
Yeah, so until last week portion. So how many
Okay.
practice we had? Like
Okay.
2 practice quizzes, I think.
Sounds good. Thank you.
Yeah, lecture 4 and 5 practice quiz.
I think there's also lecture 2 practice quiz.
Yes, thank you.
I wanted to double check on those actually. Do we have unlimited attempts on those, right? We can do them however many times we want.
If I'm
Or
understanding, is it not allowing you to do take it one more time?
the practice quiz, the lecture quizzes. Yeah.
Yeah.
I believe. Yeah. Okay. Never mind. No. I just wanted to double check with to make sure it was the same as your other classes that I've had with you.
Yeah, allow multiple attempts. It should allow you to take any number of time. All right. So
How many questions? Think for the exam?
I haven't set the question paper yet. Not more than 12, 13 questions. Let's say 15 maybe. Okay, so I think you are all not ready for the discussion. We will keep it for next week. No problem. So make sure you bring more points to talk for a long time and have discussion about it. Yes, Tony.
Did we discuss the project last class?
Yes. But we discussed, we discussed undergrad project as well as grad project last week. Check the video. If you are looking for anything specific, then we can meet in the consultation time.
And you also mentioned you want us to do the NEC table activity, but just for our own benefit, not for points. And
Yes, present it. Yeah. So that presentations we can go last week, like week 9 or week 10.
I think you said you uploaded a PDF file.
Oh, didn't I upload it? Okay, I will. Thank you. So I will upload the PDF files and you can start working on the NEC tables and present your results. So week 9 or week 10, which week we are going to lab, that week we will finish this presentation and then go to the lab. Okay. Right. So I'm done for today and open floor for questions, discussions, anything you want to have. Alfred, can you send me this video that you are recording so that I can post it in discussion forum for everyone to look at it?
Yes, I can do that.
Thank you.
Can I stop the recording already now?
Yes, you can. Thank you so
Okay.
much.
so I got all
Thank
my
you.
buddies with Power World.